So just like when we learned about, Algebra 1 problems that look something like this, and we had 2x equals 6, and then we learned about problems that looked, like this, and we had names for these different types of algebra problems. We would call this one, we might say it's linear, we might say this one's nonlinear or quadratic. Once we had classifications for these algebra problems that we were trying to solve, and someone told you, oh, you're solving a quadratic, immediately you knew, oh, okay, I'm solving a quadratic, I'm going to use a quadratic formula, or I'm going to try to factor, or I'm going to use completing the square, or some other technique that we had learned. And if you knew it was linear, you knew that, if I graphed it, it would look like a line, that we could find the intercepts, et cetera, et cetera. And so differential equations are, very similar in a lot of ways, in that we want to learn how to classify differential equations, because different classifications will give us access to different tools that we can use to actually solve differential equations down the road. And so, one of the very first tools that we have is what's called the order of a differential equation. So of a differential equation. So the order of a differential equation is given by the highest derivative present in the problem. So it's given by the highest derivative in the differential equation. Okay. So for instance, a differential equation that looks like y prime is equal to y is what we call a first order differential equation. Okay, it's first order because there is a derivative and it is a first derivative, and so that's that. If we had something that looked like, dy dx minus x times, we'll say d cubed y over dx cubed plus 3 is equal to sine of x, something that looks a little more complicated, we recognize this is the notation for y triple prime, or the third derivative, and so that implies this is a third order differential equation. All right. So order is pretty easy to talk about. It gives us a way to classify it. It's very similar to how we used to talk about the degree of a first order polynomial, or a first degree polynomial, a second degree polynomial, etc., a cubic, so on and so forth. So just if you're dealing with a first order differential equation, that's going to give us access to some different tools. And if you have a second order, third order, etc. So for instance, we can create slope fields for first order differential equations because all it has is a first derivative in it. But past being a first order differential equation, we have to use different tools to analyze and solve that differential equation. Let's see, the second term that we're going to learn about is the one that gives students the most amount of trouble. And it's this idea between classifying a differential equation as linear versus non-linear. Okay, now I want to point out something really quick, which is that in the algebra examples that you see up here, what makes the first equation linear and the second equation nonlinear? Well, you might say that, that there's a squared in the second one that makes it nonlinear, and there's a first power in the first one, and that would make it linear. And I totally agree with you. And I say, okay, well, what if I give you this equation? What if I give you sine of 3 times x is equal to 4? Is this equation linear or nonlinear? And the way that you identify this is you say, well, we're solving for what variable? We're solving for the variable x. And x is still raised to the first power, so this is still a linear equation, because even though there's sine of 3 here, relatively speaking, right, sine of 3 is just a number. Right, this is just some number. And so even though it looks crazy, you know, this sine of 3 has nothing to do with the variable that we're solving for. So even though the sine function itself is nonlinear, sine of 3 is just a number, and it doesn't affect the linearity of this relatively simple algebra problem that we have here. And so in determining whether a differential equation is linear or nonlinear, we want to focus on the variable that we are solving for. So focus on the y's, the y primes, the y double primes, etc., and make sure they are all raised to the first power and the first power only. They are all raised to the first power only. Okay, so if that happens, then we classify our differential equation as linear. So, for example, if I have 3y prime plus 2y double prime is equal to 7, this is linear because we look at all of the things that have y's and we say, hey, are those all raised to the first power? And I said, well, we have a y double prime to the first power. I have a y prime to the first power, right? I don't have y prime cubed or something like this. And so the idea is that this is what we would say a linear differential equation is. And so we could keep going. You know, if I give you an example of, I don't know, 3xy plus x squared y double prime is equal to 4, for instance. Is this linear or nonlinear? Well, again, I'm not paying attention to the 3x or this x squared. I don't care about those because the variable that we are solving for is y. And so I only want to look at the stuff with the y double prime, and say, hey, do I have anything raised to the first power? Do I have anything inside of like a natural log? Anything super weird? And since, again, the answer is no, this is also what we call a linear differential equation. Okay, so just like up above, when I had sine of 3 multiplied by x, just because I saw the sine function did not all of a sudden make that linear, because the 3 inside has nothing to do with that x, right? It's not itself an x. It's not the variable we're solving for. So, you know, we still said it was linear. Now, if I were to have given you something like this, I had said, okay, we have 3y squared plus y prime is equal to like x or something. This is nonlinear. This is nonlinear due to the fact that this y term is being squared. And another example of something that may be nonlinear might be like if I had, you know, x, y prime, and I had this entire thing cubed plus 2y is equal to the natural log of x. This is nonlinear, but it's not nonlinear because of this natural log. And it's not nonlinear because of that x in the front. It's nonlinear because I will end up having a y prime cubed. So this is nonlinear due to the y prime cubed that will eventually show up. So a good one to test your understanding would be, you know, does cosine of x multiplied by y plus the natural log of x times y prime equals y double prime, is this a linear or nonlinear ODE, or excuse me, differential equation? And the answer is this is also linear. It's linear because we're talking, it's linear with respect to y. This term, and this term, all the stuff with y's, they are all raised to the first power. They're not inside of logarithms, nothing like that. So we are good to go. But if I had given you something like y plus the natural log of y prime is equal to 6 or something, this would be non-linear. Okay, So we have classifications for these differential equations. We can talk about the order, like this one's a second order. This one is still a first order, even though it's cubed, right? It's still just the first derivative. So it's first order, but it's nonlinear, et cetera, et cetera. So we have those two out of the way. And the very last classification has to do with what we call homogeneous versus non-homogeneous. And for us, this particular classification will make less of an impact immediately because this is not a full-fledged differential equations course. This is an introduction. But the idea behind being classified as homogeneous versus non-homogeneous is if I have a differential equation, okay, so, and if we put everything with a y prime, y double prime, etc. on one side of the equation, and everything else on the other side. So everything else without a y prime, etc. on the other side. Okay, on the other side. If we only have 0 on one side, so if we only have 0 on one side, we say the differential equation is homogeneous. Otherwise, it's not homogeneous. Otherwise, non-homogeneous. Okay. And so some very quick examples to run through here would be, if I have y prime plus 2y is equal to 0. This, you'll notice, everything that has a y prime attached to it or a y attached to it is on the left side. There is nothing else on the left side that doesn't have a y on it, and everything else is on the right side, and there's only a 0. This is what we call a homogeneous differential equation. So not too bad. If I had, let's say, an xy prime plus 2y minus x equals 0, this one is not homogeneous because while I have all the stuff with y prime and y on one side, I have this leftover term that doesn't have any y's attached to it, so I need to move it to the other side to kind of get it in what we call our standard form. And so this would create the differential equation xy prime plus 2y is equal to x, which immediately gives us non-homogeneous. Okay. Right? And that's pretty much how these classifications go. So at their most convoluted and complicated, maybe we have something that looks like x squared y triple prime minus sine of x y is equal to 2y prime minus 3. And so again, the strategy is to put everything with y on one side and everything without y on the other side. So if I write this as x squared y triple prime, I'm going to move this 2y prime to the other side as a minus 2y prime. Then I have this minus sine of x y, and then equals -3. Notice the -3 doesn't go to the left because it doesn't have a y attached to it. And so this, like its full classification, would be third order. It is not homogeneous, so non-homogeneous. Okay, and last but not least, is it linear or nonlinear? Well, all of the y prime, y triple prime, y double prime, y terms, they are all normal. They're not inside of any trig functions. They're not inside of any logarithms, nothing like that. So we would say that this is a linear differential equation, right? Again, it's linear with respect to the y, not with respect to the x or the t or whatever other variable we are using. And yeah, so that's how we classify differential equations. There's more classifications we could come up with. These are the important ones. For us, the order, right? We can use slope fields on first order differential equations. Turns out solving homogeneous differential equations is not really too big of a lift. And then linear differential equations are going to be the differential equations we focus on solving a lot of times in most differential equations class, because it turns out that solving nonlinear differential equations is actually incredibly challenging. So that's the classifications. And this should be enough for now, and then we'll cover the rest, which will basically how to solve a particular type of differential equation. We will cover that in class on Thursday. So hopefully you thought these 3 videos were short and sweet. If you have any questions about anything, shoot me an email, and I'll see you all in class Thursday.